Okay, welcome. This is percent error. First of all, this formula is also on reference table T on your reference table. I know it looks a little different on table T, but it's pretty much the same thing. If you notice on table T, it says measured value minus accepted value over accepted value times 100. But this has them flipped. But the only difference is you see that there's an absolute value. So the takeaway is it doesn't matter how you subtract the two values, as long as it's a positive value. So we're just going to have a positive numerator. That's all. Always divide it by the accepted value and always multiply it by 100. On the regions, if you do not include times 100, even if you give the correct answer, whatever over here, even if you put percentage sign, if you don't have this, it's considered wrong. You cannot imply that. So please always include it. Okay? So make sure you've got your calculator, show the work, and here we go. So for the first one, we have two values. In the lab, a student must have measured 1.24 grams, probably using a triple beam balance because it only goes out to 2, or maybe an electronic balance. But the accepted value was 1.30 grams. So first we need to find the difference. So I'm going to say 1.30. And again, I apologize for this mouse. It is not great. Find that difference, divide it by the accepted, always the accepted, times 100. Okay? So what I like to do is I like to subtract the numerator. So I'm going to get 0.06 divided by 1.30 times 100. Plug it into my calculator, and I get 4.62. Now, how do you know how many significant figures to have? Well, technically, it's here. So we've got 3 here, 3 here, 3 here. You should have 3 here. Even though the numbers that you are subtracting have grams for their units, the unit for percent error is always percent sign. Okay? Second one, you know what? I'm going to skip that one because you see sign notation and you get really scared. So I'm going to skip it just because I bet that's what you're going to do. And we'll come back to it after we feel confident on the procedure. But you know what I do know? I know these are all going to be percent. So I'm just going to put those in now so I'm clear on that. Okay? Okay, so we'll come back to 2. Number 3, I see my two values. In this case, my experimental is a larger value. So I'll subtract 252 minus 225. Remember, it doesn't matter as long as you have a positive value up there. I must divide it by the accepted though. Okay, so let's subtract. And so that's going to be 27 over 225 times 100. Do my subtraction, and you should get, now it says 12, but look, 3 sig figs, 3 sig figs. Let's keep it at 3 sig figs. If you are confused about significant figures, go back, look at our notes, look at the videos, do some research, ask questions. If you are clear on the procedure of finding percent error, I'm okay, but you should know how to round to sig figs. Okay, in this case, accepted is larger than experimental, but I will divide it by the accepted. So the difference there is 0.2 divided by 22.4 times 100. Okay, that's important. This is not your final answer. This multiplied by 100. You want an answer between 0 and, 100. And so let's look for sig figs. 3 sig figs here, 3 sig figs here. Let's have 3 sig figs here. Should I put the 0 in front of the decimal place? It's a good habit to get into because otherwise I might not see that decimal place there. And, maybe I think it's a mistake or something. It shows intent. Number 5, looks like our experimental is larger than our accepted. Oops. Clear that up for you. So once again, you can see that we've got 4 sig figs. So your final answer should have 4 sig figs. Yeah, but of course this answer key did not give it to 4 sig figs. All right, so when you do your subtraction, the difference is 0.4 over 124.8 times 100. So if you should really have 4 sig figs, it should be 0.3000. That seems ridiculous. I'll give you that one. All right, now back to number 2. Do not, I mean, you can. I don't recommend jamming all of this into your calculator with the little carets and all that whatnot. Let's convert these to the standard form. Remember, in scientific notation, a negative exponent means we have a number less than 1. And if you have a number less than 1, you're going to move the decimal place to the left this number of decimal place spots. So if I have 1.24 and I need to be less than 1, I'm going to go 1, 2 spots. There's my decimal place. Throw that 0 up there. So my experimental value is 0.0124. In this case, it's still negative, so we're going to move to the left 3 spots. So 9.98, 1, 2, 3. So 2 eggs in the egg carton, 0.00998. Now, if you have problems with scientific notation, go back and look at those videos, those notes. You know, this is kind of compiling 2 different processes here. Can you work with scientific notation, and then can you do percent error? The sheet is really just testing for percent error, but I want to make sure you know both. Okay, so who's bigger? This one's bigger because there's only 1 0 here. There's 2 0 here, making this smaller. So 0.0124 minus 0.00998 over whoever's bigger, which is 0.0124 times 100. I ran out of room, but the difference is 0.00242. Now you might ask me, do I need to see both sets of this math? Do you need to plug it in, then subtract, then do it? No, if you just want to show me the subtraction, that should be okay. All right, and so looks like we've got 3 sig figs for both of those. Multiplied by 100, that is important. You get your answer, 24.2. Again, I do apologize for the messiness of this. We are making the best out of it. Okay, if you have any questions, let me know. Thanks for watching.